talking about what's new and what's next in Hive. My name is Kanta Hagleitner. I work at Hortonworks. I'm a Hive developer. I've been a long-time database developer and spent some years in Hadoop ecosystem. Previously at Yahoo, working on Pig, but now joined the Hive force and I'm working on Hive. The talk's going to be about what's currently available in Hive, what's new, and what the future will bring, and what the community is intending to turn Hive into, or how the community is going to extend Hive. There you go. All right. So first off, I wanted to talk about the Stinger initiative. I don't know if you had a chance to listen to Eric's talk this morning. The Stinger initiative is something that we launched at Hortonworks that involves the Hive community, and that is supposed to bring next-level analytical capabilities to Hadoop and then move the state of SQL and analytical capabilities forward in the Hadoop ecosystem. It's not a project. It's not a project that you can see on Apache, but it is something that the community is excited about, that a lot of people are working on. And what we're doing really is we're banking on Hive. We know that Hive is already the de facto standard for SQL processing on Hadoop, and we think it will remain to be that in the future. And what we're really trying to do is to look at latency and human time queries and make those perform in a way that a human person can interact and analyze the data with Hive without using a different tool. So there have been some bold claims out there. I don't know if you've seen it. We're claiming that we can make Hive 100 times faster than it now is, at least for some decision support workloads. But I do think that we are already backing this up with some real progress. I don't know if you've seen notes in Gopal's talk this morning, but today, using HTTP Hadoop's data platform 2.0 and using some of the benchmark things that we know in Gopal Go, where we can see that some of these workloads are already 45 times faster than when we started. So I think it's not an idle claim. I think we're backing this up with real progress. The other aspect of Stinger is enhancing analytical capabilities. So it's not just about making what you already have faster. It's also about giving you new capabilities, new SQL capabilities to do your processing on Hive and on Hadoop. With that, let's jump right in. This is I'm going to start with new capabilities first. So this is something that was already launched in Hive 10, Hive 0.10. It's a roll-up and cube operator. If you have a SQL query like on the left or on the right, if you have a typical star schema and you want to do aggregations over a number of dimensions at the same time, and you don't want to run all these queries in separation and write all these queries, you can now use rollup and queue. Rollup basically takes a list of columns in your group by statement and will progressively lump one off and run the aggregation across all of that. If you do that, instead of writing multiple statements by hand, Hive knows how to optimize for that case and do some of these aggregations at the same time. So Cube is a little bit different. Cube doesn't just take a list and lop off columns one by one, but it will actually take all the subsets of the list of columns that you've given and produce aggregates for that. So if you want to do that, to load it into a different system or load it into Excel, load it into another data warehouse, that is your one-stop shop that will do that for you. Example that you can see on the left side, it will first roll up by state and by year, and then it will roll up by state, and finally it will roll up the entire table. It will aggregate the entire table at once. On the other side, the only difference is that it will also do a roll up or an aggregation rather by by year alone, aggregating over all states. All right. If you're familiar with SQL, some analytical tasks can be really difficult to express, and SQL really does press you back against the wall sometimes and make you write inefficient and very inelegant queries. So if you look at that query, and I've shown it around in the office, you're probably going to get two reactions. The first is, what the hell is this? And the second is, don't run this. This is not going to perform. Both of these are right. What you have here is a triangular join, a self-join actually over the sales table. And then you see you have aggregates over both sides of the table, S1, S2, which are the same table, and a strange count hanging in there. What it's going to do on Hive is it's going to first shuffle all the data, do a join for you. Then it has to shuffle the data again to do the group by for you. And finally, it has to shuffle it a third time to do the order by. So that is by no means a very efficient query. But if you look at what it's actually doing, it's just numbering results on the left by certain column values, and it's producing a running total of your sales figures on the right. So it's not something that is very extraordinary or very uncommon. It's actually a very common query. In the past, Hive had some ways to make this more efficient for you, but you had to download some additional UDFs to make this run. And you had to write some really, really weird SQL. This, of course, you basically had to tell Hive to distribute by a certain hash, order the data, and then apply a UDF in a very specific fashion. Now, that's not very intuitive. This is not very SQL. It actually breaks SQL in a lot of ways. You're really specifying how am I going to have to process the data step by step rather than saying this is what the result that I want. So with Hive, the upcoming version, Hive 11, or if you want to take a look at it now in Hortonworks Data Platform 2, Alpha 2, you have overclass and windowing functions. I hope this does look more intuitive, but basically what it's doing is you're defining a window over which you're going to process these aggregate functions. You partition it by state product and order it by year. And then the sum, for instance, is just your running total. It's much easier to express it this way. The rank will rank it by date and produce this number that we've seen earlier. So definitely more in line with SQL. You're not telling the system how to process your data. You're not telling it how to distribute it, what hashes to use, etc. But you're just using plain SQL to do that. Overclass analytical function introduced in SQL 2003, the standard, some additions in a way. If you're not familiar with it, using overclass is similar to using group by, except that in group by you produce a single row for each of your groups, while with overclass you produce a result for each row in your group. You basically specify three things. You tell it partition by these columns, which, like group by, lumps together columns of the same value. You tell it, when you apply the window function, what order you want to walk through that partition. And finally, you tell it what rows to consider, what window to use. So you can use a sliding window of a fixed size, or you can continuously grow your windows from the top or from the bottom. And you can do a lot of nifty things with it. Functions that you can already try out today in the Hortonworks Data Platform Alpha 2, rank, lead, row number, lead, lag, et cetera, et cetera. So there's a wealth of new analytical functions that are there today. Additional things that we're planning to put in over the next few months is we're going to start to look at subqueries in the where clause. We're going to initially do uncorrelated subqueries, which are obviously much easier to do, but are a good starting point and very useful. We're going to do not and in clauses, which in most cases you can rewrite to a join. You can do that as a map-only join in memory, unless the in clause is getting too large. Then we're planning to do that in a shuffle join. And then another thing that we're adding and that we're looking into is additional SQL data types. That obviously facilitates integration. It makes it easier to use other systems with it. It makes it easier to use other tools against Hive that obviously expect the data types to be the standard SQL types and not like it is today in some cases, where Hive, because of its Java heritage, uses Java types instead of standard SQL types. So datetime is one of them. Char and varchar are going to come, like now that's string, that's going to probably just be an alias. The decimal type today is unbound, but most database systems expect to be able to specify precision and scale, so that's something that we're going to be adding as well. With that, on to what we've done on the plan execution on the query performance side. Now, Hive today has a number of different join implementations that you can use already. There is map joins, fragment replicate joins as they're called in SQL parlance. There is shuffle joins, there are sort merge bucket joins, and bucket joins by themselves. And right now the only way you can use them in Hive is by knowing that they're there, knowing when they should be used, and telling Hive in a query hint, in a hint to the query, that you want to use that join. So that has changed with what's coming up in Hive 11, what's already available in Alpha 2, is that you can enable the system to choose the joins for you. So it will look at whether your tables are bucketed, sorted. It will look at the size of the tables you're joining, and it will decide to pick one of the more efficient joins for you automatically. All right. Another improvement that is already available today is in trunk. It's going to be part of Hive 11 is if you have multiple joins, typically multiple, if you have a start join and you join against multiple dimensions. Dimension tables are usually fairly small tables. So with the previous improvement, they would all be converted to map joins. They would all be handled on the map side directly. They would not result in a shuffle join. But what the system is doing today, or used to do, is to string together a list of map-only jobs, one for each join. That obviously is less efficient than just doing it in a single join, in a single map task, stringing all the operators together in the execution pipeline. It's doing that in a smart way. It's looking at kind of how much memory you're allowing the system to use for that. And if your tables turn out to be too big, it will still fall back to a shuffle join, or it will group it together in a way that that you have enough memory for the map side join in each single step of it. The memory size right now is estimated from the file size, so that can go wrong, and that is well known as more of the run stats, more of the statistics of tables become available in Hive. That will be much better predictions for when we can do that. The system is very conservative. It doesn't want to fail, but it does, in many cases, pick the right implementation and merge these together. All right. When you have a join today followed by a group by, for instance, you end up with a map join first, followed by another map job that does a map side aggregation, and finally you do the group by in the reduce task. Again, a simple optimization will look for these cases and will make sure that the map join and the map side aggregation of your data happens in the same task, making it much faster to execute. Another optimization that went in is group by followed by order by. In the current system, I think that's pretty clear that that is not a great plan to execute. It will do a map side aggregation. It will then in the reducer do a group by, and then it will spin up another entire job that does basically nothing, then rely on Hadoop to sort the data for you. Now, if the keys of your order by and group by are actually similar, or the group by is a superset of the order by, you can easily combine that in a single job and do it that way. The optimization actually goes a lot farther. It looks at any reduce sync in your chain of operation, and it will see if the keys match up, if the keys are similar enough, and try to do everything in a single job. Makes a huge difference in execution time, and will make sure that you don't run unnecessary MapReduce jobs. There is a caution. There is a little caveat to this. In some cases, your reducing might have the same keys, might work on the same keys, but you might have a lot of data on one and have a high level of parallelism on the first one, and then a very low level or a small number of reducers in the second one. So the system needs to take care that if the difference is too big, it doesn't lump these together, because you basically end up running too few reducers on your job and kill performance that way. Something that is upcoming that people that write MapReduce jobs have been doing for a long time is this, and that's also a very common query, I think, when humans interact with the system and explore the data. It's doing something like group by, order by, and then limit the output. Limiting the output, obviously, you're typing a query. You don't want to have 1.2 billion records flow by. So what it is currently doing is it's trying to, the Hive is currently, when you process this query in the reducer, trying to limit the data. And it says, like, okay, I've already seen 20 records in this case. I can stop processing. But what's actually possible is you can push this limit into the map side task. You can order the values and pre-aggregate the values that you see in memory, keep the top K in memory there, and then only write those out and move them on to the reduce stage. And that obviously limits the amount of data that need to be written between your map task and your reduce task. Total order sort, something that's been available in Pig for a long time, but not in Hive. What that does basically is Hive today, if you specify an order by query, it will make sure that your last reduce task runs as in a single reducer. That means you have no parallelism there. All the data gets funneled into the single reducer, but you do get a completely sorted file. What Pig and other systems are doing is they're splitting this up. They're partitioning the key space and running the sorts in each of these buckets so that you do get multiple files, but each of them are sorted, and if you look at them in the right order, you still get the total order sort. And that obviously, if you have a lot of data, is a lot better. And the other reason why I included this in this talk is that the other improvement that we just looked at in the reduce sync deduplication, where you're trying to pull jobs together that reduce on the same key, they become much easier if you don't have to worry about steps that have to have a single reducer or that limit the number of reducers that you can have. All right, another exciting thing that is now in trunk that's going to be part of the next release is org file, the org file. It's the optimized RC file. It is another row columnar file format, but it has a lot of new features over the RC file that is currently the most widely used file for Hive processing. It has support of the complete Hive data model. The RC file before that did not know exactly what the data types of each of the columns in the file are, which means it couldn't make decisions like, I want to store this column in a certain way, I want to store or compress this column in another way. With the RC file, we can make these decisions. It does store min-max, sum, and count, so Hive can take advantage of some pre-aggregate data. It has an internal index, which means Hive doesn't have to, or the file system can help if you push down filters into the file system, scanning the data and skip blocks that are not necessary for the query. It has a row count, so finally we can let the file format participate in queries like, get count star from table, and we don't have to spin up an entire job to do that. It does have, as I said before, it knows the data types. It will pick the right encoding and compression for you to get the most efficient storage possible. And unlike some other file formats, it produces, it's a single file. It doesn't produce a number of files, which lowers the pressure on the name node and also makes integration with Hive easier. That's what the file format looks like. You have a postscript at the bottom that has information about the compression. The file footer basically contains the locations of the stripes in the file, And then each stripe is made up of index data. That's what I said earlier. That tells you if min, max, count, and whether something is present or not in the data. And followed by the row data, which is the rows stored by columns, not by rows. And finally, there is a stripe footer that is a directory for the stream locations in the file. Here you go. Why are we excited about the org file as Hive developers? Well, we can push projections down. That's already happening to some degree in Hive today, but even for complex types, we can push those down and make sure that the file format is only reading the data that we really need to process the query. We can do filter push down and have the file format skip records for us that we don't need to process the query. And finally, we can even think about longer term to push aggregates down into the file format and use pre-computed min-max sum values to process our queries. All right, next up, and I think both Eric and Arun were already talking about this, Yarn and Tez. That's very exciting for Hive developers to see this coming along. On the right side, the always-on test service is going to help us just simply spin up queries quicker. Nothing to do on our end, just reap the performance benefits. Very nice. But on the left side, what's really exciting is that test is a generalization of the MapReduce framework. So while Hive will run unmodified versus against Tez, over time, we can then start taking advantage of the more flexible nature of composing different tasks with one another. We can start just by removing some of the inefficiencies that you've already seen, places where we need to add empty map jobs, map tasks, just to get to another reduce phase. We can take care of stuff like that. But we can also, over time, fine-tune how the sorting is done, what sorting algorithm is going to be used, whether we want to write to disk or to HDFS, and things like that. So very exciting for Hive developers. Pig, other applications on top of that, I think are going to be equally excited about it. The test survey, the query startup, I mean, if you have ever used Hive, you've typed the query and you know how long it takes before you start seeing the percentages fly by and the cluster actually processing the data. With test, this is going to be much faster, as the test service is already going to be running. There's already going to be container allocated for you, so we don't have to spin up everything for every query. There's already going to be something running that can immediately turn over and start running the query. And that is done as a native Hadoop service with Yarn. It's not some ad hoc new daemons or some other stuff that we put into the system. All right, we already talked about it. A core idea of test basically is to generalize MapReduce, let you, at a more fine-grained level, choose what input and output for each of the tasks you have, as well as what kind of tasks you want to string together in your processing. So one example is for a simple query, it's a join followed by a group by. Right now, on the left side, you see we compute the join first, which means we need to shuffle the data and join it up in the reduce phase. Then we have to write all of this to HDFS and then spin up another job, go to the back of the queue, wait till this one starts up, and start processing the group by. The map jobs obviously are not adding any real value in this, but we need to do that because that's what MapReduce is and the boundaries we have for that. Now with Tez, we can submit this as a single job. We can submit the entire query at once. We can say, hey, we really need 2 shuffle phases for this. We need to shuffle for the join. We need to shuffle for the group by, and we can run this whole thing as a single job on Tez. It's not just that we need multiple shuffles. Queries can get arbitrarily complex. You can have as many branches as you want. You can write queries as complicated as you want. So in this case, you have joins with subselects and additional joins in there. again, the idea is we can remove unnecessary tasks in the system, and we can string together a graph of these tasks in the Hive engine directly and execute that directly much faster. All right, another thing that we're working at as part of the Stinger initiative is caching. Right now, for most of the Hive queries, when they run, they will load all your data from disk. There's no possibility to say, hey, this table, hey, this part of the table, or hey, these dimension tables are going to be used in every query. Make sure you always have this in memory. Or you can't tell it like, oh, really just the latest two partitions of the table, the new data is what we're going to be querying a lot. Make sure that that's in memory. Now we're thinking about ways to making this happen. Some ideas that are floating out there is pinning it in the OS buffer. Other ways to achieve that will be with a different process and pushing data in and out. And finally, execution engine, vectorization. There is I think a well-known paper by MongoDB on vectorization. The idea there basically is that the current way of most database engines, the way they process data, especially with warehousing or decision support queries, is to crunch through it row by row and then doing whatever you need on each of the columns, filtering by one column, aggregating over the next column. That's really bad for modern processing architectures because you have a lot of branches and you're basically zipping back and forth through your data. So what was described in the paper and what we're trying to bring to Hive is you basically turn your table sideways. You look at a number of columns, at a stripe of column, at a single column, at a number of values at the same time. You load it into your L1 cache ones. You make sure that your operators, your expression pipeline has no branches in it, and you just run through that block of column values once, compute the aggregate, filter out the data that you need, etc. That has dramatic effects on how fast you can run through your data on the CPU level, at least. We've seen speedups of 35x for CPU time and processing records that way. And I think that was the last slide and all that I had prepared. So if there are any questions, I'd be happy to take them now. There you go. Oh, man. My picture. Bring it up again. All right. Well, thank you very much. So if you have any questions, please go ahead. No question. Don't be shy. There you go. That's my last slide. All right. If there are no questions, I'm going to be around here. So step up if you want to talk about something Hive related. I'd be happy to talk to you. Cool. Thank you.